Yeah, hello everyone. Welcome to the string seminar. So today we are happy to have Roji Pius from IMSC, and today he'll tell us about string theory, graph homology, and gauge theories and phi.
Okay. Thank you. Should I use this one?
No, you don't.
No.
You already have.
Okay. Okay. Thank you for this opportunity. I will talk about string field theory, graph homology, and the transition from phi cube to gauge theory amplitudes. And you don't have to worry about this graph homology. I also don't understand. Just you will know why it is there. Okay, before I start my talk, I would like to thank Alok for introducing me to this topic. I'm sure that I won't be able to do any of this thing like without his help, in the sense that I don't understand any of this thing. I just go and ask him what is his result means. He explains. So he's a resource person. And this is a paper. It's based on a paper that is going to appear soon. Okay, let me introduce. Yeah. So basically, it talks about one single Feynman diagram, and you write down the amplitude. I mean, not the amplitude. Just evaluate the Feynman diagram using the Feynman rules. Even there itself, all the mathematical connections appear.
You will explain this?
I will not explain it. I will. There is a lot more things to talk about. Like I will. The point is that, do you have? I mean, usually people find it useful to have Schiwnger parametric representation. We'll see what is the context. I will tell you. It's more than just mathematics.
And when you focus on Chennai parametric representation, you're singling out like Feynman. Like, so there was no Feynman since it's 0 to 1 in Sars integral, because it would be nicer than Chennai.
Sorry, can you?
Like Feynman integral.
Yeah.
Written in Feynman parameters is worse than Chennai parameters.
No. Actually, it actually demonstrates certain more properties. Just that. Yeah. It's just that maybe you
explain this point. You said, but Schiwnger parameter is somehow special. It's not the integral, because the integral doesn't care about the parameter.
Yeah, it doesn't care. But the integrand itself, you can, if you write down amplitude or the Feynman integrals using Schiwnger parameterization, the good thing is that you can integrate out the loop momentum. And then you get a quantity like all these semantic polynomials. So people know the mathematical properties of them. Then maybe someone who knows, they can talk about the properties of amplitude. In fact, you will see that here itself, there's some non-trivial thing which we don't see from usual. Our computation will emerge, which is like very surprising connections. I will explain more about gauge theory amplitude.
The point is that you take the Feynman integral,
Yeah.
you do a loop, you do the loop integral,
Yeah,
you're left with some other representation that somehow useful.
Yeah, so I mean, people have used this. People like Francis Brown, and they study this heavily. And I'm not going to, yeah.
Just one comment is that the thing you're left with is like the word line tags.
Yeah.
So those are like the analogs of string moduli.
Yeah.
Like these Schiwnger parameters are basically word line proper time. You're converting a field theory amplitude into essentially a word line representation. That's more geometry.
Yeah. Yeah, that's true. Like all the thing that you talk about Schiwnger parameters, you can get from the modular space by taking the field theory limit. So the tensor structures that appear in the Feynman integrals of gauge theory make this thing very difficult, very hard to keep track of it. Mainly, you have in lot of diagrams. Let's say you are at very high loop, or even finite small loops. You have a lot of Feynman diagrams to evaluate, but you will see a surprising thing. Tensor structures like the propagator for a photon or any gauge boson, they have this k news appearing. So you have to keep track of all the things. So for scalar thing, you have 1 by k square plus m square, right? That's a simple structure. That is the one which actually allows you to write down Schiwnger parametric representation in a simple way. There, if you have tensor structure also, you can write down, but it's a lot of work. Let's say if you want to say something about an amplitude by resumming all the diagrams. For scalar theory, like is more manageable, but for gauge theory, it's very, very difficult. No, it's just our like usual physics thing. Like we just just indices, mu. That's it. Yeah, lots of indices. That's it.
You have to do an integral then over polynomials of this. And he said doing the loop integrals. Normally, the nice thing about the Schiwnger parameters but if you have these polynomials in the loop momenta multiplying it, then those Gaussian integrals become also doable, but more and more complicated.
Right. Yeah.
And you have to keep track of
all those things, right? And basically, you have to worry about all the diagrams. It's basically like if you have non-abelian gauge theory. Okay. Now Kreimer and his collaborators did something very, very interesting. And Kreimer and his collaborators, I'm saying collaborators because I don't know how to pronounce his third name. So they unraveled a curious relation between phi cube theory and quantum gauge theory. So what they did is really wonderful. That their claim is that they can get the renormalized integrand of a generic non-abelian gauge theory amplitude by doing some magical operation on the amplitude of a phi cube theory. And what they achieved this by any loop. I will give you a formula that will compute any non-abelian gauge theory Feynman integrand for any gauge theory. Okay? So this they achieved by using very heavy mathematics. You do renormalization. So it's not just the naive integrand that you write down. You usually using Feynman rules, you can write down an integrand for any arbitrary graph, right? So that graph you have to make sure that there is no ultraviolet divergences by doing renormalization prescription. What you get here is that you get that renormalized integrand. You can get that. Okay.
Somehow the scheme is like already built in.
Yeah, it's already built in. Basically, when you get the amplitude, it comes with a particular gauge choice. Everything is one chooses. Basically, the operation chooses a particular gauge choice. You, if you want, you can change the gauges and even the scheme. The scheme is, I will tell you, scheme is in your hand.
I think once you integrate, you don't have any double.
You don't have any divergence. So they achieved. Yeah. I will tell you, like that's a fun thing. Like you have phi cube theory, it actually will produce all the contact interaction. That's a fun thing. So how they do is by using a comparison of graph and cycle homology with BRST homology. And don't ask me about this graph and cycle homology. This is the word which I will keep on saying. I will tell you why I'm just keep on saying it. But I will show the result. And I will derive the result without using homology.
But this is in general dimension.
General dimension, yeah.
It's integrate. Full calculation.
Yeah, if you want to. So if you can do phi cube theory, then you can do gauge theory. That's it. Yeah. So what they do is they found an interpretation of Slavnov-Taylor identities through something called corolla differential. I will tell you what is this corolla differential is. So they construct this corolla differential. This is a magical. This is that magical band that I was telling about. So this operator is constructed out of something called corolla polynomials. This is a polynomial. It's a graph polynomial defined with respect to trivalent graph. That is the most amusing thing. You just have to look into the most simple graph. You have Feynman diagram. So in phi cube theory, maybe phi cube theory is part of a bigger scalar theory. You can have phi 4, phi 6, all the interactions. But what you have to do is just look at the sector of Feynman diagrams where only trivalent interactions are appearing. Okay, and this trivalent, you can define a polynomial with respect to this trivalent graph, and then you define a differential operator using this polynomial. I will tell you how this is working. I will not derive or give you more reasons why it is working from the perspective of math. From the perspective of physics, I will tell you why it is working. Okay, now yeah. So the goal of this talk is to decipher this mysterious relation. And this relation did something magical. What it does is that it shows that a quantum gauge theory, a covariant quantization of gauge field is possible without introducing ghosts. And we don't have a physics description why it is happening, how it is happening. And our goal is to find a physics description of this miraculous phenomena. And what I will do is I will try to decipher this connection using Witten's open string field theory. For any gauge theory. Any gauge theory, yeah. And let me tell you why I think that it may be possible to get an intuition from Witten's string field theory. The first thing is that Witten's string field theory is a field theoretic formulation of open bosonic string theory. And Witten showed that there is a formulation of string field theory where you can get all bosonic open string theory amplitude just by using cubic interactions. So that is one thing. That's an attractive thing. Like you have phi cube theory in the gauge theory story. Here you have some theory which has only cubic interaction. And the other thing is, if you take the field theory limit of effective action for the massless sector, it reduces to a non-abelian gauge theory. Okay, these are two things which seems like hinting that maybe Witten's string field theory is the source of all this.
Okay. Cubic is not in just the scalar, so master field.
It's for the string field. Well, yeah. So still, like there is some theory where you can get all the gauge theories from some sort of cubic interaction. So this itself won't tell you that everything will just emerge. So we have to see and we have to work out the details and see.
So when you say covariant quantization without ghost fields, you mean you will have instead of ghost fields some auxiliary fields?
You don't have any auxiliary field. You have an operator. It's basically a mathematical, well-defined operator that does the job of ghost. We'll show you like everything that ghost does can be done by this corolla differential.
The cubic string field theory has many auxiliary fields, so those will not play a role.
No, actually, I'll tell you like how to get gauge amplitudes directly from string field theory. So basically, I will not allow string to oscillate as it wish. We'll make sure that strings oscillate in such a way that only gauge particles will be produced. Yeah. We need all the string modes. I will show that we can look into a sector. You need ghost. The BV quantization automatically bring all the things. So you have a single string with all sort of string ghost numbers allowed. So that will take care of all the complications. But still, I will show that it has this magic hidden in it. I mean, I will show you. Like you'll see it how it is coming. Ghost, yeah. Yeah. So.
But in string filtered, it's where the space time ghost come from the world.
World sheet ghost, yeah.
But you will somehow find
I will show you. I will show you. Every single thing is explicit. I will show you. Okay. So now let me explain what is this connection, phi cube theory to gauge theory connection. So Kreimer and his collaborators did the following thing. So they showed that the integrand of Feynman diagrams at any finite loop order in gauge theory can be obtained from the study of two different complexes, graph homology and cycle homology, acting on a connected scalar graphs with only cubic vertices. This is the statement.
So just a clarification.
Yeah.
When you say integrand, you mean integrand when you are integrating over momentum or integrating over the
Schiwnger parameter, integrating over Schiwnger parameter. If you want, you can convert to momentum also.
No.
Yeah.
So you're thinking you have done the momentum integration,
Yeah.
and you're left with the
Schiwnger parameter. Yeah. Yeah. Right. So their statement is that somehow you just compute the Schiwnger parameterized integrand of a phi cube theory for a particular graph. It's a trivalent graph. And then act with this corolla differential. I will tell you how to construct it. For each graph, there will be a differential. So take that corolla differential and act on this integrand. It will produce the Schiwnger parameterized integrand of many Feynman diagrams in the gauge theory, which you obtain by shrinking various edges of gamma. So you have a trivalent graph. You can shrink some of the edges. You shrink all possible edges, internal edges, right?
Those will be the contacts.
Those will become the contact diagrams. Yeah. So basically what it says is that phi cube theory, by acting with this differential operator, will produce all the contact interactions, and every single thing will come out. So there also you see some stringy connection. In string theory also, like you go to different regions in the moduli space, it will give you different contact interaction. That's how Witten string field theory produces non-trivial gauge theory.
Let's say I want to get the two base area.
Which one?
I want to get the 2 to 2 base area.
2 to 2. Yes.
So the base area would have had some exchange diagram.
Yeah.
And then I would have had the contact diagram.
Yeah.
Now in this, what do I have to do? I have to consider
2 to 2 scattering in phi cube, and just compute. Maybe you can compute S channel. Okay, and then act with the differential operator. That will give you the S channel for the gauge theory and the contact interaction. Both. It will give you both.
Also the case where you don't shrink any.
Also, yeah, everything will be provided.
And if I now add ST plus U.
Well, here you are probably shrinking the internal legs.
Internal legs, yeah. Only the internal legs. That I think.
He's saying you also get the exchange gauge theory diagram.
Yeah.
Which looks the same as the exchange phi.
Yeah, that also you will get. Even that also you will
You
get.
get the one where you don't shrink anything.
And
the
you
one where
shrink up, yeah.
If you do S plus T plus Y,
No, you won't overcount, right? It's basically.
somehow get 1/3 of the whole one. Usually you would have written S plus T plus U and put 1/4.
Right. So I think
Here somehow the idea
part will be provided.
1/3.
1/3 of it. Yeah. So you sum it, you will get the same amplitude. So only by contact interaction, I mean that you will not have internal propagators. You will not see any poles there. There is a piece which has pole. There is a piece which has no pole. Maybe it comes and it will come with this factor so that when you sum over everything, you will get the correct amplitude. You will not overcount.
So the gain is like this. So if I were to consider 3 to 3 is happening, 3 to 3 is happening to the
Phi cube, yeah.
and then I use
Differential operator.
and it will give me at all loops.
At all loops, at all loops. I will give a formula that that can be written down, and you can actually use that formula. In fact, this formalism is so powerful that they could do beta function calculation up to 30 loop. It's like they're 30 loop. So they have like, this is like such a powerful thing. I don't know why people are not heavily using it. Yeah. So if there is anything wrong with these numbers, you should blame Alok. Yeah, so they have 30 loops. Yeah, and the funny thing is that this thing, formalism, is applicable for standard model also. You can use it for standard model. Yeah, yeah. Everything can be done. I will not prove now for standard model or for the theory with matter. I will right now. I will show that how this thing will come from string field theory for pure case. Pure. Sorry. Yeah. So it's actually powerful, super powerful.
But then the corolla differential will get more and more complicated.
I will, but the point is that I will give you a prescription to compute the corolla polynomial. You can put it in Mathematica or whatever. There is a well-defined procedure for doing it, and that too not so complicated.
So the left-hand side has information about the corolla.
Yeah.
So this corolla stuff.
Yeah, it will give you.
Earlier that this encodes somehow the Slavnov-Taylor identity.
Yeah,
That's
right.
why you get the
Correct coefficients, right?
Of the contact diagram.
Right. Yeah. Basically, the whole intuition for them comes from the fact that this homology has also this S square equal to 0 sort of BRST sort of behavior, and it reproduces Slavnov-Taylor identities. Basically, the entire process, they apply this trick not the way in which we do. They have a different way of doing renormalization, the Hopf algebra way of doing renormalization. All the ideas are coming from there. So it's very difficult for me to understand. What I do is I just look at the formula. I didn't understand anything, so I derived everything from string field theory. Then there's always matching every terms. So this math is beyond my abilities. That's something which there are some hopes, but there are some things which are not clear also. I haven't done yet. I think this can be done. Yeah. So okay. So this corolla differential is constructed out of corolla polynomial, which I already told. This is defined by making implicit use of graph homology. That's the reason why I'm keep on writing or saying about homology.
Differential is.
Yeah, actually, yeah, that's true. So I will give you a differential. That differential will give you amplitude or the Feynman integrands in a particular gauge, which is not Landau gauge or Feynman gauge, is something in between. If you want to go to any particular gauge, I will tell you how to do that. Basically, it's scaling the Schiwnger parameter. That will take you to different gauges. Just to show that I'm not bluffing and I'm not saying that these are very difficult math. You can just see this is a screenshot of their paper where they talk about this bicomplex. And I don't know this figure, how it is coming, but I thought I should convince you that this math is difficult. Don't think that I don't know even algebra. It's too difficult for me. Like it's very advanced math. Because, sorry. What is that? Good. Okay. So now the statement is that how to get renormalized gauge theory. What you should do is you replace the I gamma, the integrand of scalar phi cube theory, to renormalized integrand. That's the only thing that you have to do. If you know how to do renormalization phi cube theory, that will do renormalization gauge theory. That's it.
What is this F supposed to represent? You had this F in the previous slide.
Their notation. I'm just taking their notation. Sorry,
You have shrunk some edges.
I haven't done it myself. Corolla does
No,
it
no,
itself.
because the procedure asks you to shrink some.
Shrink, yeah.
And f of gamma is the new term,
F of,
because you were writing some f of gamma.
no, it's not F of gamma.
So you get multiple graphs. So
This one.
Yeah, yeah.
I mean, is there notation? I mean, it should be IF, then gamma. That's my typo.
not even sure why this shrinking graph is so important. You think it works as a
Yeah, I mean, I don't have to shrink it. It will shrink itself.
D gamma, you are saying automatically.
Automatically does it.
But I mean, the main point is that there's a physical object, the amplitude.
This is off shell. You don't have to worry only about on shell amplitude. This is off shell, complete off shell. Even the off shell amplitudes will be produced in a particular gauge.
The offset
Off shell integrands, correlation functions.
Okay, let's say case of an amplitude. So let's say I have amplitude with the right.
Yeah.
The sum of all diagonals.
Yeah.
And you're saying that to this.
Yeah.
And then sum of all.
Yeah, it will. So if you want to just look from the perspective of amplitude by resumming, that's also fine. There is more than that. That's it.
One example actually. So
I will show you some example, like at least the polynomial, how it is written, and I will tell you how to change it. Yeah. Okay. Now, to describe this corolla polynomial, I have to say something more about the graph. So some notions I have to introduce. One is the notion of half edge. If you have a graph, you have various vertices, and the vertices are connected by edges, right? Now, what you do is, so let's say you have a Feynman diagram gamma, and it is characterized by a set of vertices gamma 0 and set of edges gamma 1. And a half edge is literally a half edge. What I do is I will just take, let's say, an edge connecting AB, we'll just cut it. And then one part of the edge will go to vertex vertex A, and another will go to vertex B. So then I say that the part that connects to A is a half edge, which is connecting to A, and the part that is connecting to B will be called as another half edge of the same edge, which is connecting to B. So you write down a tuple, H is equal to V comma E, where V is the vertex to which the edge is attached. Okay, and so V belongs to this gamma 0, the set of all vertices, and E belongs to NV. NV is the set of all edges that land on the vertex V. Okay, this is the data. And
why do you need NV element?
so let's say vertex
The half
A.
edge that goes with E.
Yeah.
So now I would say it connects to A.
Yeah, one half edge is fine. I'm just saying that NV knows about all the half edges. NV is a set of all the half edges connected to a particular vertex.
Defined as the
Tuple, right?
So I've not understood now. Let's say I want to specify the half edge with
A to B, yeah.
A. So what is the tuple I should write down?
I mean, is that the edge
E I should write down.
edge AB, that is E, and just say A.
So you should also say which edge is part.
Which edge is part? Edges? Yeah. So I will just say that's a half edge, plain half edge. Yeah, that's yeah. Because like I do it that way, I know that I am doing the other way, because when I start from string field theory, we usually talk about propagators and edges. So this language is not so familiar for us. Like usually we start from edges. So I think we'll just cut it and. Yeah, so that's true. Yeah, yeah.
There might be a case where you have a loop diagram where this is just uniquely specified. Symmetry factor.
Yeah. So you have to always mod out the symmetry factors when you do the computation. So this itself is not completely. I mean, there are various symmetry transformations that you can do. So that's why I'm just doing. I mean, I will tell you that I choose a particular edge J. Let's say the edge connecting A and B. So let me call that as H. That's a half edge connected to vertex A. Now, there is an edge that is coming, that's a predecessor of this half edge, H, which is the edge connecting A and B. That I will call that as H minus, another notation. And the edge that is coming after H will be called as H plus. That's a successor.
These are the planar graph.
I mean, any graph you can.
But you have a non-planar, is that an ordering?
I will have an ordering. I will tell you. That's the next thing.
No, the successor you are saying is the remaining part of the half set.
No. Successor means from here onwards I will restrict to one vertex. So that's the main goal.
Okay.
I want to look at the vertex. I don't want to see the entire diagram.
You're talking of around the vertex some orientation.
Yeah. So if I say if it is,
I think Ashok's question next, because in general, unless you're planar, what does it mean to, unless you have a ribbon like graph-like structure, what does it mean to specify an orientation?
so this is an additional thing that you put in.
Okay,
For
so
this,
you make some arbitrary choice.
yeah, we can make an arbitrary choice in a throughout. I mean, when we talk about string theory, like you'll see that everything is inbuilt. This is already a ribbon graph. So yeah. It's not necessary that, yeah. I mean, I have to be consistent. If I choose a orientation for each vertex, I should stick to that. That's it. I mean, that's my current understanding. Yeah. So if I want, I can choose a cyclic order. Cyclic order, yeah, on each vertex.
It's like if you have this IQ interaction, you can impose a cyclic order. Right? And then the non-penalty will come from how you join.
Yeah, how you join. Yeah, that's true. Yeah.
Yeah, but in this case, he's not distinguishing between planar and non-planar.
No. I'm right now. I just want to focus on each vertex. So the point is that this corolla differential I'm going to construct is by referring to each vertex, and the actions are done at each vertex. Okay. So now, so I think the notations are clear. So you have a half edge H, and then the predecessor will be called as H minus, and the one that comes next will be called as H plus. Okay, that's the notation. And next thing is the notion of incidence matrix. So we can order or direct all the edges of gamma. We do that in Feynman diagrams because we have to specify how the momentum is flowing, right? So the flow of momentum will give you an ordering or a direction for each edges for the graph. And that can be captured by this matrix, which people call as the incidence matrix. So what it does is, this is a convention. If I say that if a vertex V is the endpoint of an edge, if the edge is landing on that vertex, I will give the number -1. So I'm specifying the matrix components. Okay, so the matrix has two directions. Like one is the wedges. What are the vertices, and the other one is the edges. Okay, so I call that component EVE as -1 if the vertex V is the endpoint of the edge E, and +1 if the vertex V is the starting point of the edge E. Okay, and 0 if the vertex is not talking to that edge at all. Okay, so you can
Putting orientation on each edge.
yeah. So arbitrary orientation. That's like I'm just thinking that momentum is flowing in a particular way. Okay, and so by now the point is that once you construct the incidence matrix, you don't need this graph. You can actually construct that graph with a particular ordering. So the entire data will be hidden in this incidence matrix.
This also doesn't matter whether planar or not.
No, yeah, it doesn't matter. It's just flow of momentum. Arrow means like I'm saying that let's say E3, the one that connects A and D. I'm saying that it starts from D and ends at A. Basically, the momentum flow is from vertex D to vertex A. That's a convention. So let's say actual momentum flow is not that way. Then the momentum is like minus of that. So that's an additional thing. If you look at this E8 column, so each column tells you where the edge is starting and where it is ending. Okay, if for certain columns, if there is no two entries, only one entry, that means it's self-loop. So you see that it starts from D, E8 is starting from D and it ends at D. So that's
one by convention.
That's -1 also, yeah.
But whenever such a thing doesn't happen, the column should all act as zero.
Right, that's the point. Okay, now, so given all this data, I'm going to decorate my trivalent graph. So what I will do is consider an edge that is landing or incident on particular vertex V. To that, that's a half edge, right? To that half edge, I'm going to associate three variables. Three variables are AH plus, AH minus, BH. So just think of some X, Y, Z. Three variables. They come with this notation AH plus, AH minus, and BH. H plus, you remember, it's the successor of half edge H, and H minus is the predecessor. Okay, so for each, you choose a particular half edge, and for that half edge, define three numbers: AH plus, AH minus, and BH. Now, for each vertex V, using these three variables, I will construct an object. Okay, so for each vertex, there will be some number of half edges. Since we are only interested in trivalent graph, there will be three half edges, right? For each half edge, you will have AH plus, AH minus, and BH. And H can vary, right? From, I mean, you have 1, 2, 3 half edges. So H will vary depending on which half edge that you are looking at. So take all those quantities, do this.
These are some numbers.
These are, right now, think of them as some variable. I will do something after
But,
this next slide.
You have not defined what yet.
I haven't defined. There's some variables.
For each half edge, there are
Three variables. That's the point. Yeah. And then
Vertex.
each vertex has three.
Each vertex there will be three vertices.
No, no.
Right? Because
for each
That there will
half
be 9.
Oh, because you will put a separate variable when you count it as a.
Yeah. See, H is summed over NV. NV is a
H is not the same as when you
change the edge.
when you change the edge. So
Right.
even though it's the same edge, which is now a
Right.
successor to
Another
you
edge.
give a different variable.
Exactly.
So
Yeah.
you give nine variables.
Vertex has 9 variables. At least now there is no relation. I'm no way connecting them right now. So like you said, there will be 3 variables for each vertex. And what I do is I take AH minus and sum with AH plus, one thing, and then multiply with BH. On each vertex V. So let's say, so take this particular vertex. Okay, there is this half edge, this one, there are 3 half edges. Now just focus on one half edge, this particular half edge. And I say that I mean, for this half edge, there will be 3 variables. Those are AH minus, AH plus, and BH. Okay, and then take that AH minus, AH plus, sum them, multiply with BH. Now similar 3 variables are there for this edge and this edge. Do the same thing and then just sum them. That will be an information about the vertex because I have summed it. Okay, and then so that is the calligraphic V. That is an object for each vertex. Now we have to worry about the loops, right? So there are there could be many loops. So for this figure, there is one loop. So for each loop also I will define a object using the same variables that I already defined. So what I do is I consider half edge HCJV. I have to tell you what is HCJV. HCJV is a half edge that is incident on one of the vertex of gamma, and that vertex must be part of the loop. So here all these vertexes are part of the loop. And then I have to look at the half edge that is incident on that vertex but should not be part of the loop. So for instance, 0 means it's the vertex that is part of that loop. You remember gamma zeros are the set of all the vertices. So that's a notation. So if I say 1, that's an edge. If the notation is 0, superscript is 0, then that's a vertex. Yeah. So CJ0 means all the vertices that is part of that particular loop CJ. So here these vertices are part of that loop. Now I consider HCJV. By that I mean it should be it's a half edge that is incident on the loop, but it should not be part of the loop. That means this can be an HCJV. This can be an HCJV, and this also can be an HCJV. But none of the loop, the edges that are part of the loop won't be HCJV. That's a.
You should do this for if you had, say, a sunset diagram.
Yeah.
Okay, you're doing only trivial.
Yeah.
Okay, sorry. Yeah. If you had any diagram, you have to do this for every possible cycle in the.
Yeah, every possible cycle. For every cycle, you define this object. Yeah, every 3 cycles. So
only 3 cycles, or it can include 4 cycles?
or cycle. Can you tell me what is the 3?
if you have two triangles, you also go around the
I
whole
will. Yeah. You take any loop.
any loop.
Any loop.
So you take the inside triangles as well as the outside.
Yeah. You for every single. I mean that will come. For now, I'm just defining an operator, right? For any loop. Then later, how I will use that I will tell you. Okay. So for each loop Cj, I define this particular object. What I have to do is I identify these vertices, these half edges, and then for half edge, I have the two variables, right? The moment I choose an h, I can have variables ah minus and ah plus. So here, just replace that h with hcjv, okay, and take the index row. Row runs from plus minus 1. So basically, it means you take this one half edge, and then the variable that is associated with this half edge is ahcjv plus or ahcjv minus. These are the two things, right? Predecessors and the successor. Just multiply ahcjv row for all the vertices that is part of that loop, then sum or plus and minus.
You do this such that you've already quotiented out by the automatic, or will you do this for every symmetry?
I will do it for everything, and at the end I will quotient by the automorphism group. Similar to what we do in Feynman calculations. Okay, so you have this.
Precise distinction between H plus and H minus.
H plus is the successor of some half edge. H minus is the predecessor. Basically, if I have this as H, then the predecessor H minus is this half edge, and the successor is this half edge. That's it.
Left or right.
Right, left or right, yeah. Okay, so what I have done is for each vertex in the graph, I defined an object, and for each loop also I defined an object. You don't have to remember all the details.
So if a certain age, half age, is the successor of something and predecessor of something, they have the same age. Is that right? Or
No. Those are thought of as different variables.
I see.
Yeah.
So this plus and minus that you associate to age.
Yeah.
These are not related to successor or predecessor. This is different.
No, they are successor and predecessor. So here HCJV can be this half edge. It cannot be this or this because it's part of loop, right? So then when I define the predecessor, that will be something, the index will be that of the edge that is living on the loop. Okay? It will work. I will show you. Like. Yeah.
The external one you will be considering as BH, and then AH plus and AH minus will be associated with the half edges which are
Loop, part of the loop. Yeah.
Okay.
Right.
That's why I mean it always carries a sign.
Yeah, right. Exactly. Okay. Now, once you have all the objects, you can define the Corolla polynomial for a pure Yang-Mills theory. Okay. So what I do is I have some term C0, then minus C1 plus C2 minus C3. So now I have to tell you what is CI. Okay. CI of a particular graph is defined the following way. The definition looks a bit complicated. What I do is I first look at all the vertices that is not part of any loop. Okay. Take that, and then for that, for each vertex, there is this object calligraphic V that I have defined, right? So let's say if I choose a particular index I, then that also involves some certain sum. Okay, what I do is take the Feynman diagram. There can be so many loops. Choose I number of independent loops. Okay, so there can be many different choices, right? So if I choose a particular graph, there can be some, let's say a graph having 10 loops. Let's say index is 5. So that means I don't have to, at the same time, I don't have to look at all the 10 loops. I choose independent 5 loops out of it. Okay, that's a particular choice. That once you made that choice, then you can talk about the thing that is inside the sum. Okay.
So the number of independent loops is what you normally call the number of independent loops.
Yeah, that's true. That's the same. So you don't have to look at all the independent loops at the same time. So depending on how many independence loops that you look at, you have the index. So here, the first term is C0. Diagram can be a loop diagram, but the first term never care about any loops. It do the calculations as if it is a tree diagram. Okay, so there what you do is you just look at all the vertices, take the object that I have defined for you, then just multiply all of them, right? So if there are 100 vertices, all the 100 vertices will have the object, and then just multiply them. So that's the first term in the series. For the second term, I have to look at one independence, one cycle, can be any cycle. Okay, that can be done in many ways, right? If there are 100 cycles, there could be various choices of choosing independent cycles, right? So, and then what I do is, in that diagram, I first look at all the vertices that is not part of that cycle. Okay, and for them, I take the object that I have defined, VV, and then multiply all of them by making sure that that vertex is not part of the cycle. Polynomial in this variable, AH plus AH minus, so those variables.
But so in the C1, for instance,
Yeah.
So I'll sum over all the, so supposing I have two loops,
Yeah.
and I would sum over the smaller one, the other smaller one, but also the bigger one.
Bigger ones, yeah.
I'll sum over all of them.
Yeah.
Sorry, I thought you said independent one.
No,
But the point is, an independent thing, it means that if I have more than one cycle, yeah, let's say if you, yeah, everything is independent. All possible loops. If I have,
L of gamma is the set of all
let's
loops
say
in
let's say
gamma.
you're doing the nested self-energy pipe.
Yeah.
Two loop self-energy.
Yeah.
So it has like this one bubble and then
Right.
a bubble sitting over it.
Right.
So how many will you do if you're doing in C1? How many will you do?
all cycles,
How many are there?
you have to just look at it.
Two or three.
Yeah.
Because there's this,
Correct.
there's this. Like if you don't count for the symmetry factor, there's three. So 5 cube, you are doing nested. 5 cube, 2 loop nested. 2 loop. Yeah, 5 cube, 2 loop, self-energy nested.
So you have to look at all the pieces and then, yeah, everything that you have to look. 3 loops, 3 of them, right? All the 3 of them. That means this sum will be 3 sums.
Which diagram are we? I think it will be.
I think you're talking of this.
Yeah.
Oh no, I was thinking about nested. This is
Okay.
this is overlapping.
It's actually, I know everyone is a very high loop.
No, but this is either of them.
Yeah.
Before that, even at tree level, it seems like a remarkable thing.
Yeah.
We have no Schiwnger parameters.
Yeah.
You take 5 cube amplitude, then you can.
Yeah.
So I know you said you would show it, but we show that example. It will help a lot.
So then,
Done all this graph theoretic thing of very high 2 loops.
I mean, then I have to open my paper, which is not completed. No, I haven't included in the this thing.
But before we do,
See, now I will not do any computation. I'm just giving you the structure, and I will show you at abstract level. I can prove it. It's a homework, yeah. and if you want to see the explicit thing, it's there in Alok's paper. I can compute it. It's just that it will take a lot of time. Like,
at this level, polarizations haven't appeared.
sorry.
Polarization
Uh,
haven't appeared.
see the
You now
derivative.
associate a differential operator. to
Yeah,
this
yeah.
polynomials.
So this here there is no index now. There is no Lorentz index. The next slide I will show you that each AH plus AH minus and those will be replaced by some derivative with respect to momentas.
So just a clarification.
Yeah.
So in this loop, you are not allowed to traverse the loop multiple times.
No,
Just it has to be a simple closed loop.
simple closed loop, right? Like we do Feynman integrals, right? We'll just look at basically what Ashok said. You just look at the loop momentas.
The loop momenta, there are only two independent ones here.
But the point is that if I take one particular term, C1, then I have to worry about all the loops, right?
But when he's taking C2, he will take only one of them.
Right,
When
right.
he takes C2, that I didn't understand about pairwise disjoint.
Yeah, so this one, if I see, so if this diagram,
Is there a C2 here or not?
yeah, this C2 basically says that there is one thing. Yeah, I think there is nothing.
No, but that's
No. There is only one thing.
There's only
one.
There's no C2 contribution coming.
No, there's no C2
There's
contribution.
no
That will
C2.
stop.
They have to be disjoint means that there are no vertices in common. at all.
I mean, no edges common. There is no edges common.
But vertices can be. No,
Vertices can be common.
But there are no 4 vertices.
I mean, that's true. There are no 4 vertices, so when vertices won't be common. Right. Right.
Sorry, I'm a bit, just for C1,
Yeah.
what loops are we keeping? Because we are keeping some.
Maybe I will give you a different way of thinking.
Just here.
These loops, the additional terms are ghost contributions. If you look at gauge theory, so these are the contributions from the Feynman diagrams. If along some edges, along some loops, if ghost is running, they come with negative signs, right? Because they have the anti-commuting stat thing, so they will always give you minus signs. So these additional terms are coming from the ghost contributions.
So minus C1 is the ghosts are coming along that.
Along that loop, exactly, along that loop, right? So
My question was very simple.
Yeah.
So you have here 2 independent homology cycles.
Yeah.
The third one is just a linear combination of it.
right.
So which homology sums are we keeping and which ones are we not?
Now you can take.
One is taking.
Yeah, so I take this loop, that's one term, and for the second term I can choose this loop, and for the third term I can choose this one. All are like, because ghost can run in different loops, right?
So those are all C1.
All C1, all C1.
C1 you will get
So there are sum of 3 terms in C.
Right. So basically the point is that let's say along I number of loops, ghost is running. This particular CA is giving you that contribution. Okay.
Yeah, that makes it clear.
Yeah. So it's basically replacing ghost with a differential operator. That's it. So this sum actually, when they write it, they say that Ci in the full corolla differential, this I index will be summed from 0 to infinity. Okay, then it may look like an infinite series and may not look like a polynomial. But the point is that the moment you fix the number of loops, this polynomial will this sum will terminate at some point. That point is the maximum number of independent loops that you can have.
Is that obvious from the definition?
From the, yeah, because see, the sum should be Cj pairwise disjoint. That itself will terminate it.
So for L loop, it will not terminate at CL, right? Probably terminate at something greater than CL.
For L loop, it should be,
L minus 1.
yeah, you have to see how many independent,
Sooner than that.
yeah. Okay, so I'll give you a simple example, one loop self energy diagram where all these ingredients are coming. Okay, so if Suvrat wants to see the 2-2 diagram, you just look at the factorization of one of the edge. That will give you the, right? So you just cut one, say edge 2. That will give you 2-2 scattering. Okay, so let's say you consider this one loop self energy diagram. First, you have to mark all the vertices. So mark A and then B. These are the 2 vertices that you have. And you can mark the edges. So this is edge 1, edge 2, edge 3, edge 4. You have to worry about all the edges, internal and external edges. Then half edges you define by saying that, see, this edge 1 has 2 parts. One part which is edge gamma, that is going to vertex A, and edge epsilon, that is going to vertex B. Similarly, the external one, this is what he was asking. The external one is always just a half edge. Okay, H delta. And then similar thing you can do. So this is how you define vertices, edges, and half edges. Now, once you have this data, then you can ask, let's say for vertex A, what is the object? That object is given by A H alpha plus A H alpha minus multiplied by B H alpha. Okay. Similarly, you do that for all the half edges. For H alpha, we did it. For H beta, you did it. You can do it. BH beta, AH beta plus AH beta minus. Similarly, for H gamma, BH gamma, AH gamma plus AH gamma minus. H, I define here. I denoted one of the half edge with an index H gamma, H beta. That's how I define each half edges. It's just a notation. There is nothing more than that. Okay. Yeah. AH beta plus is some variable. You can think of that as some x.
So the H beta plus is the successor to the
Yeah, right. H beta plus, I mean, at the end, they will be, at the end, you have to identify that H beta plus is H alpha. So that at the, so that you, sorry? That depending on how you oriented it, right? So at the end, you don't have 9 independent variables because you know that some of the H alpha plus might be another H beta. So that identification will come so that you won't have 9 variables. No, I mean, just to write down things, this is how you write down things, right? Then you say that, okay, H alpha, AH alpha, beta is basically this at the end of the computation.
End of the day, products are only 3. The 9 will degenerate into
Yeah, that is equivalent to demanding
vertical.
yeah, so momentum conservation. So when you do all this computation, you never assume momentum conservation. Only after applying the corolla differential only you will apply the momentum conservation.
H alpha and H delta will not know about mass.
Sorry?
H alpha and H delta
Yeah.
will not know about the mass of the external body.
I mean, they at this point they don't even know anything. The next level only I will tell you, right?
I presume you don't want to set them equal now because for taking derivatives, etc.
Yeah.
You have to treat them as independent.
Exactly, right. I have to do that way. So, and for the loop thing, what I do is I have to see how many vertices are there, which is part of the loop and which is not part of the loop. Okay. So you can see that all the vertices A and B are part of a loop. So they are all part of a loop. Now you have to see how many independent loops that you can have. Okay. You can have one loop because there is only one loop. And when you construct the corolla, you have to first treat as if there is no loop. That is the first term, C0. Now in the second term, you have to remove that independent loop and see how many vertices are left. So here no vertices are left. So there is no contribution coming from those kind of vertices. Only contributions are coming from the loops, right? Now you have to see what is that contribution associated to a loop. Associated to a loop, you have to take the half edge that is incident on the vertex of that loop, but not part of the loop, right? So such vertices are H alpha and H delta. There are only 2 such half edges satisfying all the criteria. So take that H alpha, then for that H alpha, you can define AH alpha plus and AH alpha minus. Then for H delta also you have similar thing. So you just multiply H alpha plus AH delta minus delta plus, then similarly AH alpha minus AH delta minus. This is how you compute the corolla polynomial. A simple prescription. You have to just see what is the rule. Put in Mathematica, that will also construct the polynomial for you. So it's not a difficult definition.
You eventually identify H gamma and H epsilon.
I mean later, only later at the end of the computation. So I have to define how I'm going to construct a differential out of it. This is a polynomial, right? Now the next step is to define the differential.
What is the orientation?
So here I have chosen, so it's already clear, right? H alpha, so yeah. So here actually I can say that so the moment I clearly say what is the orientation, then you will start identifying H alpha plus H beta or H gamma. So sorry?
So you're summing over cycle.
Yeah. But there I already choose a cycle, right? And then only I define it.
But in ribbon graphs, you define cycle.
Right now, my data is just this much. I'm not assuming there is a ribbon graph. I'm just taking a normal.
You put a cyclic ordering. Then you get. I think it was not defined.
Yeah, I haven't defined it.
No orientation.
Right. I haven't. Basically, I don't have to orient it right now. It's just that before or after.
Yeah, so that means there's a cyclic ordering.
Yeah.
At everyone.
Yeah.
There's like a cyclic ordering.
Cyclic ordering. Yeah. In each vertex, I can define. Right. And the point is that I mean I can consider even non-planar because of the fact that I haven't told you that every vertices has to be ordered in this particular way. This is just a trick.
Like trace phi 2 interaction and with that you can build on planar graph.
Exactly, right.
But still it can be embedded on a surface, so it's a fat graph.
Fat graph on a surface, run maybe any arbitrary Riemann surface.
But the issue, for example, if you take
Yeah, nothing has happened, right? It's just that I defined a polynomial. just define a polynomial. No physics yet. It's just for now. You cannot question me. These are my what are things I'm just giving you. Just accept it.
My point is the cycles you're summing over depend on the orientation that you study.
At this point, this description does not any orientation.
Right.
Seems to be right. You have to
I mean the point.
for some orientation.
At the end, like when I do the computation, at the end of all the procedures, I have to say which one will be mapped to what. Yeah. Yeah, because see, I haven't told you what is H alpha plus means. I haven't told you what is H alpha plus, right? I haven't told you H alpha plus is H gamma or H beta. I haven't told you. This is just a polynomial I have written down. You can see 9 variables here.
Later on, when you declare the orientation, it will identify H.
Yeah, right, right.
That info will go in whether you identify H gamma with H.
Yeah, right. When I have to do it. So right now you don't have to worry about anything. So now I will define the corolla differential using these variables. What I do is for each edge E, I define or introduce a real variable T. This is the thing which is becoming a Schiwnger parameter. So I introduce the Schiwnger parameter for each edge and a momentum vector to that edge. So now the physics slowly start coming. So you introduce a real variable T, which is a Schiwnger parameter for an edge, and a momentum Ke mu. That is the momentum flowing through that edge, and a Lorentz index mu e. Okay.
Now, it seems that you said earlier we had only the Schiwnger parameter. Then we had done the momentum. Why the momentum?
It can have external momenters, right?
External momentum only. Internal implies there should be no momentum.
That's why I'm saying I haven't specified the momentum conservation. I haven't imposed the momentum conservation. I'm just keeping the momentum as it is, like as if they are independent. Only at the end of the computation, that's part of prescription. When I do string filter, you'll see that that's also part of, it's also like that. So I haven't introduced the momentum conservation. I mean, you can keep the momentum integral there, right? There is no problem if you want.
I can have indication about Schiwnger
But,
parameter.
and the momentum. And so what I do is for each half edge H rho, I will define a differential operator, A H rho. Okay, right now there is no connection between all that small letter A and calligraphic H rho I'm introducing here. So this is a differential I'm defining. So rho can be plus or minus, right? And epsilon H rho is the incident matrix that I have. And 1 by T is the Schiwnger parameter associated with that edge E. And del by del Ke is the momentum derivative that is flowing through that edge. Okay, these are things that we are familiar with. So,
What is DEH?
sorry,
T.
so I'm just saying that for each half edge, I'm just defining this variable Te. These are notations.
So then it should be each half edge.
To each half edge, but they can be identified later. Sorry, half edge associated to that vertex, right?
What is this rho?
This rho is taking value plus or minus. So this, sorry, yeah.
Really, this is for each predecessor and each.
Yeah, so later, like they'll be like that. And sorry, yeah.
We can go so just to understand something. So there is one way the property is just a description of the scalar property.
Right.
The very old textbooks, that's how it is.
Yeah.
But here something more is happening because you also get the fourth one.
Yeah, yeah.
Could you please explain using this roughly how that is?
That's happening. If you want, you can maybe let me see. So what that you can understand only after doing this replacement. I will tell you from where it is coming. Okay. So so these derivatives are there, momentum derivatives. So each moment. So what I will do in the next is the following. So there's one more thing I have to define. For each half edge, I will introduce this metric tensor, this eta mu nu, right? And then what the corolla differential is obtained by doing this replacement. AH rho will be replaced by calligraphic AH rho. So the variables that I introduce will be replaced with this differential operators, which are like momentum differentials. And BH will be replaced by the tensor. the eta mu. So this is how the tensor structure is slowly coming. Okay.
Does it depend on ordering prescription? Earlier you just have some numbers floating around, some variables floating around,
Right.
but now you have derivatives.
So here also I haven't sorry. Yeah.
All the deltas, these are derived.
Yeah.
Oh, they're all different.
So once you have that differential operator, you can you get the corolla differential. Now, like coming back to Suvrat's question, what I do is the following. So you have the Schiwnger parameter representation of phi cube theory. So which will be like e raised to minus t k square. There is no mass, and these operators are going to act on this object. Okay. So when I act with one delta k, this will bring down 1k. When I do second time, that will bring down one more k nu, so that they will form k square. So that k square will kill the propagator that is there in the phi cube diagram. That's how you get contact interaction. So all the propagators will be killed by this sum of the combination of this differential operator. So this shrinking is happening through this derivative. Okay. So these are the color indices are the adjoint operators associated with the generators of the gauge group. So this can, each diagram, it always has this structure, right? Color factor actually comes out.
IQ already had a factor.
Yeah.
It's today's time. Now you are taking away
So now, so as I keep on saying, we don't assume momentum conservation until the corolla differential is acted on the scalar integral. Okay, and so the statement is that this operator, this whole thing acting on a renormalized integrand, produces. Yeah.
I might have got a K mu.
See, there is this tensor index B, right? That is eta mu.
Yeah, so just difference as I because you one of the derivatives acts on the first K that pulled up.
Yeah, right, exactly.
That's how you get it.
Yeah.
And you think that correctly combinatorically gives you all
the right. And the contact interaction, like you said, part of the contact interaction, so that when you sum over all the channels, you get the correct full amplitude. That's like really wonderful, right? Somehow it just happens for any gauge theory. That's the point. There is something which is independent of any specific gauge group.
That's the gauge group is kind of all gone anyway.
Right. But the point is that how the photon will self-interact, right? If you have U1 theory, photon will not self-interact. It's like a free theory, right? I'm looking at pure gauge theory.
Probably just a factor that color indices.
No, it's not just that, right? You will not have any interaction at all. If I look at Yang Mills, sorry? I mean, it's just a one-dimensional representation. Yeah. Yeah. So if you are looking at trace of phi q, I'm just saying if I have the usual Yang Mills, the Maxwell theory. I mean, so the point is that if I have to do the computation, I don't have to think that this is adjoint representation. I just take the simple phi cube theory.
But there is a color.
I mean, this is something which you can put in, right? Or you can think that the theory is adjoint. In string field theory, that it comes like that. Yeah, but yeah, so
divide it into classes.
Right. So I think like at least
Which color?
Yeah, because even Feynman diagram or phi q automatically will have the corresponding color indices.
Yeah. So in string theory, that's how it happens. You have an adjoint phi theory. Scalar theory, and all the gauge groups is actually the gauge group that I already attached to the phi cube. Okay. So now
Actually, will give you in some Feynman-like gauge.
Not Feynman-like gauge. Basically, yeah. So it's between Landau gauge and yeah. So let's say the psi parameter is 0 for Landau gauge and 1 for Feynman. So this one is half.
But sorry,
That, and you can go to Feynman gauge by scaling this t, Schiwnger parameter. Right.
Answer around what? Answer around some Lorentz like or like del dot A plus kappa A.
I mean, here I don't have the gauge field to begin with, so I don't know. I haven't
How do
seen.
you know that it is half and half?
So the point is that when you compute, you get a result, and then from there you can read out the propagators.
Why did you need that half in that two? I mean, in that the differential operator, you have 1 over 2. Why did, instead of 2t, if I just put t, it would have been psi equals to 1?
Yeah, right. No, just scaling the t. Just scaling the t is the
changes the psi of
Yeah.
our psi gauge.
yeah.
So if you put psi, if you remove the t, you put psi.
Yeah,
there.
it will. That's true.
Why choose half? I mean,
I mean, just like that. I mean, it doesn't matter. Like you can change if you want. Yeah. No, the point is that see, this t is integrated, right? Integrated from 0 to infinity. If I scale or not, it doesn't matter. Answer is not going to change.
So if you scale or not, the answer won't change. But if I just change,
Sorry?
change the gauge.
There is some extra factor, right? The overall factor will come. But that's a statement. You rescale your Schiwnger parameter, it will take you to consistently rescale it. It will take you to different places. You should rescale every Schiwnger parameter. Okay. So and the point is that this is not done for toy models. This is something that can be done for anything, including standard models.
Get some sense of. You're saying that t is integrated.
Yeah.
In the previous case, you'll have some measure that's like dt over 2t.
Yeah.
Typically in world line integrals, that 2 is like the orientation reversal of the world line.
Yeah, symmetry.
Some symmetry factor.
Yeah, so here you have to put symmetry additionally.
No, just
Symmetry factor.
this O is he's saying is coming from the half side. Is the psi equals to half?
What I'm saying is, if it is the measure is dt over 2t,
Yeah.
that's natural because the log z of a single scalar is half log something. So that half log, that half is this one half.
He's saying it is not that. He's
Yeah.
saying you have to put that half separate.
See, the point is that
Symmetry factor.
see this d gamma, that is also depending on, I mean, that's the thing that I was telling you, right? So that depends on the Schiwnger parameters, right? D gamma, the differential operator depends on Schiwnger parameter. I gamma depends on Schiwnger parameter. Now I rescale it, then it will just take you to different case.
Somehow by normal scale Schiwnger parameter, that's why scaling the moment.
No, the point that you do, and after that, the corolla operator also get rescaled. So that's why it's not by just saying that I just rescale a Schiwnger parameter directly. You see the gauge difference. You have to.
Yeah, it's adjusted because the B doesn't have the, so B is always eta mu nu. So it's the relative factor between the B and the K mu.
Right. 15 minutes. Oh, 15 minutes.
Last question before this, about this last time. Generalization standard model. So now you're saying even if you have like fermionic matter. Or
Yeah. So then the corolla differential will be generalized. That can be done. And these are already known. This is a work done in 2012, and 2016 it is like by that time like people know a lot. In spontaneous symmetry break theories, everything is known. That's a surprising thing. That's a funny thing. I don't know like why. I haven't told Ravindran. Like I just told Alok and then I'm telling here. Yeah, so I think that's what Alok also says. Like all this thing will be.
Alok has talked about it. So.
Yeah, Alok knows about it. And Kreimer.
Alok knows it, Diva will know it. Alok talks to Nima a lot, right? So you would have definitely told Nima.
See, I can tell. So this paper was written in 2012 and the citation is only 34. So such a remarkable work. So it's, I think, very.
Sorry, which paper are you talking about?
The one, the Kreimer Sars. 22. Yeah. Okay, so the aim is to understand how one can get a physics picture of all the thing that I'm doing or whatever we have discussed. Yeah. It's basically like that. Yeah. I mean, that's why I'm saying most of the things are discussed in their papers or like previous papers, which I'm not able to decode. But string field theory, all things are already inbuilt because it's quantized using even the classical action. I will just use the classical action. That's also an action that satisfies BV equation. So all the things are inbuilt. So we don't have to decode it. Like these people, I mean, if you want a clear understanding, I think that's why I'm keep on saying I don't understand the math picture. They have talked about BV equations and all the stuff, even by using Hopf algebra, which I can't explain.
Is there some simple way in which this can be generalized to off-shell correlators of gauge invariant?
I mean, this is for off-shell, so you can gauge invariant
composite operators.
composite operators.
So when you will not have tri-variant, I mean, when you don't have just simple like trace F to the.
I think it's possible. Like from string field theory, what I have done, I think it is possible. I mean, you will see that all this many things, right? So I think it should be possible. I don't know. I haven't analyzed it yet. Yeah. So far, whatever discussed, I was just telling you this is what happened, and this is a place. I mean, up to that moment, I don't know each point to give you like how they constructed, what are the constraints. But now from here onwards, I can tell you like how everything is happening. So my aim is to understand the physics of it. Okay. So this mathematical structure is tantalizingly close to open string field theory. And this cartoon I put just to tell you that usually it doesn't happen to me. Like mathematical structures immediately give me some understanding. Okay, this might be happening. So for me, mathematical physics papers are like doctor's prescription. I find it very difficult to decode it. Somehow the prescription was written in such a way that I can understand. So the aim is to decipher this mysterious relation using Witten's open string field theory. So I'll briefly review like what is Witten's open string field theory. So open string in flat 26 dimensional background is described by sigma model of 26 free scalars together with a BC Gauss system of central charge minus 26. So this is the action, world sheet action, and this is the BRST operator. JB is the BRST current. Now you can construct the Fock space of this world sheet theory by considering all operators of, I mean, all states of this kind, where A are the oscillators for the field X, and B and C are for the Gauss system. Now, so this is a standard thing that is, I think, familiar to all of you. And then we can consider a D-brane configuration where there are n number of D-branes sitting on top of each other, so that's equivalent to introducing Chern proton factors. And you see that you can write down vertex operators, right? And associate a Chern proton factor from the basic states that you define. So Ka is the state which is sum of Kij lambda ij. Basically, here the extra degree of freedom that you have for the open string is encoded in the state from which you are constructing the vertex operator or the excited states. Okay. So these lambdas can have 1 to n square number of independent lambdas. That is coming from the fact that the string field must be real. So it makes lambda a Hermitian operator. So you get n square number of independent thing, and this lambda transforms under a UN transformation. So that UN symmetry will be there in any amplitude computation because always trace of lambdas will be coming. So amplitude will have this UN symmetry. So all space-time fields will transform as adjoint of the UN symmetry. And this global symmetry of the world sheet theory will be elevated to UN gauge symmetry in space-time. Okay. So these fields B, A, phi, these are the target space fields, and they transform as a adjoint of UN symmetry.
This phi is the tachyon.
Phi is a tachyon. Phi is a tachyon. A mu and alpha are the massless fields. So the classical open string field theory action proposed by Witten has only one kinetic term and a cubic term. So this is Witten actually told us how to actually construct it in principle. He gave a geometry, and then later Gross and Javicky showed how to convert into oscillator representation so that you can actually do calculations. Okay. So there's a kinetic term and there is an interaction term which can be calculated. I will show you how to get all those things. And this story is correct for classical string field theory. The moment you go to quantum string field theory, I mean, any loop you compute, there will be a channel through which closed string will be propagating. Basically, open string just combine with a closed string. So you have diagrams of this kind. Because of that, you don't have enough degrees of freedom to construct a consistent quantum theory. Closed strings are missing. So at loop level or quantum level, you won't be able to, I mean, at least so far, I don't know, maybe Ashok knows, there is no consistent quantum BV master action. So no quantum action. But the point is that for us, we just need to calculate amplitudes. For that, you only need classical action. You don't need quantum action, quantum BV action. So now let me tell you how Witten vertex is constructed. So in string theory, like the amplitudes are constructed by just letting string propagate, merge together, and comes out, right? So this is what is happening here. So naively we think that the two endpoints of the open string just combine and then give you a third string. Okay? So naively that's one way of thinking of this interaction. What Witten said, said is that you don't need. I mean, this process can happen in many ways. There can be 3 strings joining together to give you 4th string, 5 string joining together to give you 6th string, and then can be loop, and all the things can be there. What Witten said is that all those complicated diagrams can be constructed using his propagator, which is a Schiwnger mechanism, and a cubic interaction. Only 3 strings will interact. That will cover the entire compactified moduli space of Riemann surfaces with boundaries. That's a very non-trivial thing. And the Schiwnger parameter that appears in string field theory, open string field theory, give you a different coordinate parameterization of moduli space. Okay, I won't be able to finish. Okay, so what Witten said is that, see, the interaction should not be thought of as endpoints are just combining and giving you third string. That will not do this. If you take such an arbitrary choice, they will not be able to cover the entire moduli space. Only if you choose in a specific way. What he does is he take 2 strings, find midpoints, and then say that half of one string will be joined to half of other string, and then give you third string. That is equivalent to saying that the 3 vertex interaction should be thought of as correlator computation on a disk with 3 punctures, and that 3 punctures are at the boundary. 3 puncture diagram should be thought of as a minimal area diagram. Basically, you should be able to put a metric on it, and that metric should be minimal area metric. So when we do amplitude calculations in string theory, you never choose a metric, right? So choosing metric is equivalent to choosing coordinates around punctures. So if you have to construct string field theory, you have to choose a metric or local coordinates. So Witten says that if you choose a particular metric, then you will be able to cover the entire moduli space, and which can be thought of. This is the diagram, that minimal area diagram. So basically, flat strips are joined. 3 flat strips are consistently joined at midpoint. That is the Witten's vertex, which can be mapped to disk with punctures, 3 punctures, or half plane with 3 punctures at the boundary. All these are equivalent, and the map also is very clear. We know how to map a flat flat string to this triangle portion of the half disk. That map is known. Because of that, Gross and Javicky could construct the Witten vertex explicitly. So the V2 that I have written down here. So this is the action, right? There's a kinetic term and a cubic term. So there is a V2. V2 is an element of H, tensor product of H. Take 2 copies of H and take a tensor product. V2 is an element of that. And V3 is an element of take 3 copies of world sheet Hilbert space and take a tensor product. And V3 is an element of that. So that particular element knows about what is that diagram. Okay, so that Jevicki and Gross constructed, and they give the explicit expression. So these A are the oscillators associated with X mu field, and B's are the oscillators associated with the B field, and C are the oscillators associated with the C field. And the coefficients CMN and CN, so that's also known. So this V2 is used to consider the propagator. Basically, BP is the inner product of two string fields. And V3 is the one which knows about the Witten vertex. That is more complicated. So the CMN has very simple structure. It's basically diagonal matrix. Delta NM multiplied with 1 minus 1 raised to n. Okay, this is a diagonal matrix with plus minus 1 entries. Now here the V.
Contains information about the BRST operator.
Sorry.
The CMN will contain information about the BRST operator.
BRST operator is separately added, right?
But it's part of V2.
Yeah, it's taken outside.
So you are saying V2 you calculate and
then yeah, exactly.
V2 is in the BP sector.
Yeah, V2 is the BPC in this product, right?
These numbers depend on the metric you were talking about.
That is again like this V2 will be thinking of like flat string propagator. So that's a flat metric. Okay, for V3, it knows about the fact that this 3 flat strings are just joined. That information is there in this expression. Where it is hidden? It is hidden in these coefficients that are appearing here, which are called Newman coefficients. So every magic of string field theory is encoded in Newman coefficients. And we will see that. In fact, the magic, the way the Newman coefficient is behaving is what actually provide you all the magical relations that we found. V3 from V2. V3 and V2 are like, they are different. If you want V4 and V6 take, then you can construct out of V3 and V2.
Is this the Strebel metric only?
Strebel metric, yeah.
Okay, from strip to however.
Yeah, right. So basically, then the point is that Strebel map, you know, for each part, you have to combine them. Okay, now once you have the action, now our point is to compute the amplitude. So we'll just look at the propagator. We have the string propagator, which is written using V2. You take V2 and then do small variation. That will give you V tilde. And how you get V tilde, what we have to do is take the expression for that V2, replace all CMN with C tilde Mn. And C tilde Mn is e raised to minus mt CMN. So this T is the Schiwnger parameter of the Witten string field theory. Okay, this way is slightly modified. And L0 you know, and B0 also is known, right? So this is how the propagator looks like in string field theory.
What is the meaning of this e to the minus?
So basically, what you have to do is you take a string, let it propagate. Basically, it's by acting with L0, right? E raised to T L0. You let the string propagator for some time, Schiwnger time T. So that effect is already encoded in the propagator. Right?
L0 is the oscillator number n. That's why.
Yeah, exactly. Yeah.
So M is the eigenvalue of L0.
Yeah, right.
I mean, it's the mode number.
Mode number,
CM,
exactly.
The same m, right?
Yeah, exactly. It's the same.
Same m.
Yeah.
Minus 1 minute.
-1 minute. Yeah. So whoever wants to leave, they can just leave. I will. So I will just try to finish.
So I think let's be clear. I think it's a fair point that Feynman is making. It's more than 1.5 hours.
Yeah.
So maybe if there is some quick summary you can give in 5 minutes.
I can give, yeah.
You can give that, and people who want to leave.
Yeah,
leave, and
they
then
can.
we
Yeah,
continue
exactly.
with the people who want to.
Sure. So maybe I will quickly tell you that massless fields in open bosonic string theory has this string field expression where only a mu and alpha appears. They are the massless fields. So alpha is like the Gauss field, and a mu is like the gauge field. And you can construct the low energy action, which reproduce all the quadratic, cubic, and all those interactions. So they take this particular form. You compute string theory amplitude, and then you just write down the Lagrangian that actually reproduces the amplitude. So now this doesn't look like something that is familiar to us, right? A very complicated expression. Then what people have shown, like Ashok and all people have shown, that you can find a field redefinition of this A mu and to some A hat mu, which is a very complicated field redefinition. And these people have, Washington Taylor and his collaborators, already computed what should be the precise coefficients. They did it for non-abelian gauge theory. For simplicity, I'm just talking about the abelian gauge theory. Then after this field redefinition, one can show that the action that I have written down will take the form which is exactly equal to the action that you obtain from DBA action, okay, by just doing alpha prime expansion. So do the alpha prime expansion. This is after field redefinition. This is the action that you, which is very familiar looking one, right, in terms of F mu. And if I take strict alpha prime goes to 0 limit, I get the Maxwell action. This is the gauge theory. If I have non-abelian, I get the non-abelian gauge theory. And this is one reason why I'm looking at open string field theory. The low energy alpha prime going to 0 limit is precisely the gauge theory of our interest. So if I know how to calculate amplitudes where string is only excited to gauge fields, that is precisely the gauge theory amplitude, right? So alpha prime expansion, because it's very different. Now, I'm just saying that I can take this action and do the alpha prime expansion. Whatever I get will match with whatever I get after field redefinition. It's just a way of telling that people have tried to check it, whether DB action can be derived from, at least the alpha prime expansion can be derived from the string field theory computation. Yeah. So Yang-Mills amplitudes, how to compute Yang-Mills amplitude from string field theory. So why should one even look at string field theory? Like, you have gauge theory, you know everything, you just compute it. Why should somebody learn string field theory and do this calculation again? Okay, naturally one may think. Usually string field theory or string theory calculations are very challenging. So computation using low energy effective action for massless fields are manageable. So am I mad to do this? But we will see that or the open string field theory can unravel a rich mathematical structure hidden in the Feynman diagram calculus. Now, if I want to compute the gauge theory amplitude and forget about all the massive excitation and tachyon amplitude, what I do is I consider Feynman diagrams in string field theory. Usually, any Feynman diagram in string field theory will have all states in the Hilbert space propagating through their internal lines, especially loop. Everything will propagate. And what I will do is I will choose A mu to be the external states and allow only the massless field to propagate along the internal edges. That will give me gauge theory amplitude. So now the point is that, is it possible for me to make sure that string will not oscillate such that it will not go to higher excited state? That I can do only because of the fact that this theory has cubic interaction. So every vertex, every edge is in my hand. Every edge is obtained by gluing the Witten cubic vertices. So there I can make sure that only certain states are propagated. Right? In closed string theory, it's not possible for me to do, because even the contact interaction will have loops. There I have no choice. I cannot just simply do it. There I have to do something else. Anyway, this is how I compute gauge theory amplitude. Now to get the gauge theory amplitude, I will do one more trick. What I do is I consider a coherent state, a generating state, which has a property that I construct this state, then take derivative with respect to this J mu's and JB's and J's, the calligraphic JC's. What they will do is they will pull down the oscillators of my interest. And after that, I set this J to 0. Then what I get is I get the state I want. Okay. So this is a simple trick. And basically this allows me to.
There is a full contact interaction. Comes from massive state exchange. Right?
Massive state exchange.
Like you go to low energy limit and it gives a full contact.
Yeah.
So from the beginning, if you remove those,
right? They will come with alpha prime corrections, right?
There is some alpha prime in the numerator and denominator. So there is m squared in the denominator, but also I have m squared in the numerator.
Okay.
So remember correctly, you need the massive state.
So usually, like, this is something which I learned from Taylor's paper. All those massive excitations are giving you higher corrections. the expansion of dBA terms. The initial term doesn't require. So that's why I'm just looking at the strict alpha prime goes to zero limit. If I don't take strict alpha prime goes to zero limit, I mean, then the point is that if I take strict alpha prime goes to zero limit, all the massive excited states are really well separated. Yeah. That's something which I will show you. This happens the same way Corolla does it.
You don't need the higher massive
No.
swing state at all.
No, I mean, that is already encoded through this generating state. But when I pull down, I mean, whatever is computed, I will show you all those things can be computed. And effectively, what I should do is just do that computation, full computation, and then just take derivative with respect to J's. So maybe like whatever remains, they will stay there. So we will see. Basically, the basic idea is to use this coherent state. That does the magic for me. Okay, if I don't use the coherent state, it's very difficult to get anything. The moment I use coherent states, then things are very explicit. So what I do is now I take the string propagator. Now introduce a notion of half edges. So propagator, I just try to split it. What I do is that for each half edge, so any edge you take, they will be connected to some, if they are not external state, they will be connected to two vertices, right? So I split them and then say that to each half edge, I associate a state with index 1, A1 mu h. This is the state associated with the A mu field. And this one is a state associated with the alpha field. Similarly, for the other part of the half edge, H tilde, which is part of the same edge, I will introduce the second copy of the state, A2 mu h and B2 minus and C2 0. So now the propagator can be thought of as gluing of these half edges, okay, which is given by the eta mu stress tensor and e raised to minus alpha tk square. Similarly, for alpha, the propagator is given this way. Okay. Once you have that, I can just write down a formula for all tree diagrams. So this is the formula. So basically the point is that I write down trivalent graph, and then through the edges I allow only the states of my interest to propagate, and those states are pulled down by these operators associated with each half edges. Okay. So if I do the calculation and set j equal to 0, I will get the tree level gauge theory amplitude or gauge theory Feynman integral.
But somehow this is different from if you take the Wilkinson perspective.
Yeah.
And then restrict to massless fields from the beginning.
Yeah.
That's not what you are doing.
No, that's not what I'm doing. I just do computation. Everything I do at the end only I take alpha prime goes to 0. That's why I'm saying this coherent state does the magic for me.
But you said that you are restricting on the internal propagator.
Yeah.
So, right, you are restricting only to the massless.
Yeah, only internal propagator. There I can always restrict, right? When I compute the Witten vertex, so I have to evaluate the Witten vertex. There I don't do any restriction. I do the computation for so basically the vertex will be phi, the string field will be replaced by the generating state, the generating G, and I have to compute it explicitly, fully, without taking any alpha prime goes to 0 limit. I have to make sure that I'm not taking alpha prime equal to 0 limit. The moment I take alpha prime goes to 0 limit, all this thing will be trivialized. I won't do that initially. I will keep everything, do the computation explicitly. This is something which I can do simply, like, because this is just oscillator calculation, squeezed coherent state computation. Formulas are known, one can compute it.
Information vertex is there.
It's there. This is a trivalent graph having some number of vertices. All vertices will have cubic interaction. That is there. Okay, and then I have to join all the vertices using propagators. So these propagators I am replacing by this differential operator. That's it. So I will get the gauge theory diagram. And at the end, I take alpha prime goes to 0 limit. Okay, I don't take alpha prime goes to 0 limit to begin with. Then the point is I am already in the gauge theory. Then nothing will happen. I won't see anything. So now the point is that there is an interesting feature in Witten string field theory. I take A square, basically two gauge fields and its interaction with alpha field. This alpha is the other field in the massless sector. Yeah, basically the ghost. Yeah. This one. Yeah, alpha and A mu. Yeah. So basically the redefinition, okay, before that they integrate out that alpha field. So I keep everything. And so this A square and alpha interaction I can compute. And because of the property of Newman coefficient, that actually vanishes. In full string theory, it just vanishes. So that means there is no contact interaction that involves A mu's and one alpha. A square alpha is not there. That is interesting. That actually does the following simplification. One can draw all the Feynman diagrams, and then I demand that external legs are gauge field, A mu. And alpha A square interaction is vanishing. That simply means that you cannot have any ghost field, alpha field propagating through the internal. So you can try to see here you have A mu, here you have A mu. And if you want alpha to propagate, you need alpha A square term. That is not there.
So it will propagate only in the loop.
Only in the loop. Yeah, only in the loop it will propagate. So this makes my previous formula simple. I can simply drop all these terms. Okay. What I have is only derivative with respect to this J mu's. Okay. Then we will see how corolla is emerging. So this is something like take that previous formula, do a slight rearrangement. I can put all the derivatives on the vertex. Each vertex will have this Witten vertex, then this derivative acting. Okay. Now I can evaluate what exactly is this expression. This is given by this expression. As I said, like these are like coherent state computation for harmonic oscillator. Something which is very easy to do. One can evaluate. You see that there is a term in the exponential which comes with two j's, quadratic in j. There is a cross term k and j, and there is a term where k square is there. And the calligraphic j's are already in square form. So what I do is I just complete the square. I can just do the complete, I can complete the square with this math bbj, and math bbj is combination of the generating parameter j and the momentum. A momentum vector and j vector is there. So this momentum vector is not simply the momentum that is flowing through the edges. It's a combination constructed out of Newman coefficients. These momentum vectors are finite in number, right? But I can construct infinitely long column vector by multiplying with V0n. Right? N is running from 0 to infinity. So basically, I construct column vectors out of this the momenta that is flowing through edges. So basically, this fact actually
Those ends are higher massive states, right?
those ends are higher massive states.
They are all higher massive.
I just say that these are coefficients, Newman coefficients for any value for n. One part of the coefficient is 0. So V0n, so that V0 can be contracted with the momentum associated with 0. Okay, so then you have the simple chain rule, which says that you have a function defined this way: f of x equal to a of x into e raised to minus y plus e square. Then they take derivative with respect to y, and then you set y equal to 0. This is exactly equal to ax del by del xn e raised to minus e square x. Right? You can forget about this y altogether. That means all the j mu derivatives can be replaced by momentum derivatives. Not precisely the momentum, is a combination of different momentums.
Somehow j and k come together and you are saying that.
Yeah.
Differential expression j and set j equal to
So,
equivalent
to taking momentum derivative. Yeah. So then the one who knows everything, Newman coefficient tells you that, see, I have this nice property. For VHH, that's 0. VHH plus, there is this non-trivial number. VHH HH minus 0, 1, you have a non-trivial number which is exactly negative of this number. That says that the derivative, which is replacing the generating parameter, has this property that if I have an edge, for that edge I have a derivative. That is given by the derivative of momentum with respect to the predecessor edge and the successor edge. So this is almost like the corolla structure. Okay. Now what I do is I just substitute this expression. Sorry, corolla, but I have a g. I can rescale my g, right? The interaction strength. I haven't written down the g angles, right? I will just dump everything in that. Okay, so basically, after using this, what I get is the string field theory Yang-Mills amplitude expression is precisely corolla expression. Every single thing matches. And when I do the calculation, I also didn't use momentum conservation. I have to use the momentum conservation only at the end. Okay, so every single structure matches, every single piece of coefficient, everything matches. So you get the corolla out of string field theory. So this is now we'll show loop-like diagram. There also really magic happens. So what happens is that you can construct the loop diagrams where there is a graph attaching to back. This is one tadpole diagram, some simple example. And what one can show is that, like Ashok was saying, unlike in the case of tree diagrams, Feynman diagrams with loops can have internal lines where this ghost field is propagating. Okay, this is due to the fact that you have a alpha square interaction, which is not vanishing.
Also, transverse scalars, they can also propagate. Or you have to use space filling there.
I'm just taking space filling brain. Like I haven't studied that. I have to. Maybe it will work out. I have to work out the details. So then you consider a two-loop diagram. Okay. So in this two-loop diagram, one can ask along how many edges alpha the ghost can propagate. So let's say throughout every edges the ghost is propagating. That requires you to have alpha cube interaction, right? Then again you can calculate whether there is alpha cube interaction or not in string field theory. You can show that because of the properties of Newman coefficient, that also vanishes. Okay. I mean, it is constructed out of BC fields, so they have wrong statistics. That's why it's called ghost.
It's Grassmann or alpha is Grassmann.
Grassmann, yeah. Yeah. Yeah, this is a space-time ghost. Yeah, right. So now the point is that you can work out all the details, like the fact that there is no alpha cube interaction, but still have alpha square interaction. That simply means that whenever you have two loops having common edge cannot have two loops having common edge cannot have both alpha propagating. Gauss field cannot propagate through two loops which are intersecting. So that is precisely what corolla says. Okay? So you just have to work out the details. You should see that exactly same formula will be reproduced. So basically the point is that what corolla compute is the gauge theory for the string field theory effective action. The gauge theory, they treat as if it's the string field theory effective action. And that's basically related to the original gauge theory through a field redefinition. So if you compute amplitudes, field redefinition should not change the result, right? So you will be reproducing the same result in a slightly different way. And string field theory give you a very complicated field redefinition, which shows the corolla structure. I mean, if you want to have the right, so, but I think there is a field redefinition. Yeah, it just means what is your external state, what combination. So, but the point is that if you sum over all the Feynman diagrams and choose AMU which matches with the original AMU, right? You should be getting the same thing. But definitely for physics result, both will be same. On shell amplitude, like we can, right?
In your case, alpha was B minus 1 C1.
B minus 1 C1, yeah.
B minus 1 C1.
Yeah.
So that should also be paired with a vacuum itself.
B minus 1 C0.
B minus 1 C0.
C0. C1 is already there in my vacuum.
But B minus 1 C0 is
There is a C1 already there.
C1 is already there. So it's not SL2R invariant vacuum.
okay.
C1 into SL2R invariant.
So this is just C0 on vacuum.
Just C0 on vacuum, right?
Okay. This
C0
is
B
like
minus 1.
Yeah, this is like the auxiliary.
Auxiliary field, right? This is what actually I integrate out
So
to get a dB.
Then this is Grassmann.
Grassmann, I mean, yeah. So only thing is that's true. It's bosonic degree of freedom, but when you compute loop level, it is constructed out of this BC derivative. So there will be fermionic nature coming. Alpha is, if I look at as a field, those are like bosonic target space-time field. But in the computation, you have to explain how the minus factors come, right? If I have to compare with the corolla structure, corolla comes with minus factors. I don't know what is it. I see.
I got confused. I thought the ghosts are the vacuum and B minus 1 C or vacuum.
Yeah.
Those are the ghosts.
B minus 1. Here it's
Sorry, not
B minus 1 C0 acting on.
C minus 1 C on vacuum and the vacuum. Those are the ghost fields. Space time ghost fields.
Yeah.
So this is an mechanism. This is space time mechanism. Yeah.
So this is the.
Yeah, because
this action
the whole thing is multiplied by C somehow in.
Yeah, this K is multiplied with C1. C1. Here also, we already start with a gauge. To write down a gauge propagator, you have to choose a gauge. That's the Siegel gauge. Yeah. So the point is that everything sort of works out, and it gives you the corolla at the loop, or any loop number.
If you put n spatial grid,
Yeah.
you get SUN.
UN case, not SUN, UN.
UN.
Yeah. And if you have,
So what I'm not completely understood is how you do the projection so that only the massless ones.
no, the point is that this derivatives that I'm acting on the coherent state actually pulls down only those fields. That's why I'm doing projection. That's the reason why I use coherent states. I mean, it's, I mean, so the point is that you have to just look at what these people have done to get the effective action is that, so you take this alpha, okay, and then what they do is they don't have derivatives on alpha, right? So they could just integrate out. Yeah. Yeah. I need alphas. Alphas are propagating.
No, but also you need the. But you also need the space time. In this language,
Yeah.
there will be B minus 1 K.
Yeah.
Right, that will be 1, and then the C minus 1 C1 C minus 1. Like that is that.
Yeah.
Those
So
will
that.
also be mass level zeros.
I mean, I just repeated what Taylor has done.
I think they are doing the level.
No, they do loop level also. They have done the tadpole computation. I mean, then I have to cross check it. Like maybe that particular thing we have to. Yeah. Right. Okay. I will check it.
May I suggest that you show the
Last
future
is done.
direction,
It's
that
done.
we can
Done.
continue the discussion.
Yeah. So yeah, that fact I have to verify, but I think it should work out. So the conclusion is that connection between phi cube and gauge theory naturally emerges from Witten's open string field theory and the field theory limit. That's what I kind of think. And this sort of shows that there is some sort of interplay between graph homology and string field theory. And it looks like it's very efficient in computation also. Usually the impression is that string field theory are not so good in computation. Okay, so now the future directions are like you can try to include fermions. For that, you need to consider the superstring field theory. And if you want to study the spontaneously broken gauge theories, you can separate the d-branes. And there is this idea of Hopf algebraic renormalization, which is again a mathematical procedure to do the renormalization. This I think maybe I haven't checked that maybe you can introduce in string field theory a scale factor through stubs, which is basically saying that you rescale the local coordinates that you use. So this can be done. This is already done. So one has to just do computation there in that open string field theory with stubs, and see whether the structures matches or not. And one can try to generalize this to arbitrary spin fields. And then other thing is like whether this way of understanding amplitudes can tell us something about positive geometry. And I have a conjecture there. My conjecture is that positive geometry is the space of all string theory configurations, including kinematic data. So there are some way, sort of reason why to believe this, which Alok and Nima, they have computed that they have this positive geometry way of calculating amplitudes. And the positive geometry comes with certain coordinates. These coordinates has some, one can try to do a diffeo there. And this diffeo, what it does is it actually take you from one theory, amplitude of one theory to another theory. So my feeling is that it might be a transformation which you do in the space of string theory configurations. So if I change the string theory configuration, we know that the effective theory changes. So there's a high chance that we can understand or give a string theory interpretation of positive geometry. And then this last thing, which is like something which I kind of obsessed with, like because of his training, Rajesh's training, that maybe one can try to combine the world sheet duality and renormalization ideas to derive string theory dual of gauge theory, because of the fact that this string field theory already has the graph data. And maybe you don't have to go to ribbon graph by hand, like it already comes that way. And also the fact that string field theory knows about renormalization through the stub parameter. Maybe one can use the perturbative understanding of the string theory dual and the non-perturbative statements about renormalization versus radial direction. Maybe one can try to combine these two ideas to get understanding of string theory dual of some arbitrary gauge theory. It's a very ambitious thing. So that's just the entire. Thank you.
Thank you for a very nice talk.
Yeah, yeah, right.
Strip it of all this other stuff, the fields and the speaker.
Yeah.
And then the first unbreakable relation between the string vertices,
it might be there. I don't know. My background is so weak in that direction, so I don't know. Maybe it should be there. Sorry. Thank you. Thank you. This week, I have to understand this thing.